This is the lecture for Module 4 of Unit 4. This is the chemical equilibrium unit, and in this module we apply chemical equilibrium principles to insoluble ionic compounds. Alright, again we're going to apply equilibrium to the solubility of insoluble ionic compounds. And here you have to understand I'm not actually talking in contradiction. You will remember the insoluble salts you learned about from Gen Chem 1. It turns out that all these quote-unquote insoluble salts are slightly soluble with varying degrees of solubility. So if you have a lump of lead iodide compound at the bottom of a beaker of water, for example, you will remember that this is an insoluble salt from Gen Chem 1. This insoluble salt can break apart to form lead and iodide. In other words, here's the equation for the dissociation of the ionic compound in water. But the salt is quote-unquote insoluble or slightly soluble, so K for this reaction is very small, 7.9 times 10 to the negative 9. In other words, the left-hand side is favored. Alright, however, even though K is small, you should be able to write down the equilibrium expression for this reaction. Build an ice table and solve for the concentration of lead and iodide, which will give you the molarity of the lead iodide, or its molar solubility, the concentrations when equilibrium is achieved. Okay. The way to solve this sort of problem is to assume the initial concentration of the aqueous species is 0. Or in other words, imagine a hypothetical situation in which we just introduce the solid to the water. Alright, naturally, the reaction will proceed to the right, but not very small, not very far. And you can build an ice table to solve for the equilibrium concentrations after it has gone sufficiently to the right. Right. You may attempt this before continuing. Alright, now again, we should illustrate that this is a straightforward application of what we know about equilibrium. K for this reaction is 7.9 times 10 to the negative 9, and in the equilibrium expression we have the concentration of lead and the concentration of iodide squared. Note that since lead iodide is a solid, its concentration does not appear. Once again, our assumption is that there is no ions initially, and that the concentrations of lead and of iodide are equal to 0. The reaction has to proceed to the right, so the concentration of the lead will increase by some amount x, and the concentration of iodide increases by some amount 2x. And the sum of the initial and change is the equilibrium concentration. So at equilibrium we have concentrations x and 2x. Right, the goal here from a mathematical point of view is to solve for x. And so we plug in the x's into the equilibrium expression. 7.9 times 10 to the negative 9 is x times 2x squared, or 4x cubed. Right, this gives, when you solve for x, divide both sides by 4 and take cube root. X is 1.25 times 10 to the negative 4. Now, as always, we need to remember what x means. And we can see that this is the lead concentration. Note that if we were asked the iodide concentration, that would be 2.5 times 10 to the negative 4. Since we are asked for molar solubility, or the number of, well, the concentration or moles of lead iodide dissolved, there's 1 lead per lead iodide, so the molar solubility is 1.25 times 10 to the negative 4. Alright, here is an exercise. Find KSP of silver phosphate from its molar solubility, which is 1.8 times 10 to the negative 5. Here is the reaction. Silver phosphate, which is insoluble, dissolves a bit to silver and to phosphate concentration. Alright. Now, the SP in KSP stands for solubility product constant. This is an exercise. It's essentially an inverse of the previous problem. In the previous problem, you had KSP and solve for molar solubility. Here you have molar solubility, and you will solve for KSP. You should be able to do this, stop and attempt before continuing. Now here's a solution. The equilibrium law has K equal to the concentration of silver ion cubed times the concentration of phosphate ion. Remember, the solid sitting at the bottom of the beaker does not appear. We set up a table, and the initial concentrations would be 0. The equilibrium concentrations would be 3x and x. Notice that I don't have the change table in this ice table. But to go to equilibrium, the concentration of silver will increase by some amount 3x, because stoichiometrically the amount of silver that is formed will be 3 times the concentration of the phosphate formed. X is phosphate in this case, and since there's 1 phosphate per silver phosphate, X will represent the molar solubility of silver phosphate. Alright, then KSP is 3x cubed times x, which gives 27x to the 4th. Right, we know the value of x, so we insert that and obtain the value 2.8 times 10 to the negative 18 for the equilibrium constant. The question, will precipitate form, is probably the most challenging type of problem involving equilibrium of ionic compounds. For example, will a precipitate form in a solution containing 0.10 molar lead nitrate and 0.060 molar sodium chloride? And this problem gives KSP for lead chloride. Alright, now before we proceed to the math, we would have to think about, for a moment, how does a situation like this arise? We have a solution with 0.10 molar this, and 0.060 molar sodium chloride. The way such a situation can arise, a hypothetical situation like this, is from mixing a certain volume of 2 solutions, a sodium chloride and a lead nitrate solution. Alright, let's proceed then with the data we have. The reaction we're concerned about is a solubility reaction for lead chloride, or the dissolution of this insoluble compound. Lead chloride goes to lead and 2 chloride. And the equilibrium expression would be 1.7 times 10 to the negative 5 is lead concentration times chloride concentration squared at equilibrium. Alright, if the concentration of lead in the solution times the concentration of chloride squared is greater than 1.7 times 10 to the negative 5, then the reaction quotient Q is greater than K. The reaction will go to the left, and a precipitate will form. Alright, in this case, the lead concentration times the square of the chloride concentration is 0.1 from the lead nitrate times 0.060 squared from the sodium chloride. Total on the calculator from this is 3.6 times 10 to the negative 4, which is greater than K. So yes, a precipitate will form. Okay. Here are a couple of precipitate problems you can attempt. Well, it's a precipitate of silver chromate form, and here is a K for silver chromate, an insoluble compound. Will a precipitate form if the concentration of silver is 2 times 10 to the negative 4 and the concentration of chromate is 3 times 10 to the negative 5? Alright, this is the easier of the pair of examples. Will a precipitate of silver chloride form if solutions A and B are mixed? A is 50 milliliters of 0.2 molar sodium chloride, and B is 50 milliliters of 0.2 molar silver nitrate. It may seem obvious, but we are going to assume that the volume of the two solutions mixed is going to be the sum of the 50 plus 50, or 100 milliliters in this case. Okay, so in part B, the result of the mixing will be a 100 milliliter solution. Note that PPT is a common abbreviation of precipitate. Alright. First attempt A, and then attempt the more difficult problem, which is B, before proceeding. Now here's a solution for A. K is equal to silver concentration squared times chromate concentration equals 9.10 times 10 to the negative 12 at equilibrium. If we take 2 times 10 to the negative 4 squared and multiply it by 3 times 10 to the negative 5, the result is 1.2 times 10 to the negative 12. Note Q is less than K, so no, under these conditions, a silver chromate precipitate will not be formed. Alright, now in our silver chloride example, we have, as I said, a dilution of solutions. The final volume is 100 milliliters. So the final volume is doubled, and the final concentration of silver and chloride are halved. Alright, which means the concentration of silver and the concentration of chloride are each 0.1, not 0.2. Q, the reaction quotient, is 0.1 times 0.1, or 0.01. Q in this case is greater than K for silver chloride. Remember, K is 1.8 times 10 to the negative 10. So the answer is yes. Okay, here's one more example. Will a precipitate of barium carbonate form if 100 milliliters of 6 times 10 to the negative 5 molar barium chloride is mixed with 100 milliliters of 4 times 10 to the negative 5 molar sodium carbonate. Again, we're going to assume the volume of the mixture is the sum of 100 plus 100. Remember, PPT is a common abbreviation for precipitate. Alright, because the volume are double, concentrations are each diluted to half the original concentration. So the barium concentration is 3 times 10 to the negative 5, and the carbonate concentration is 2 times 10 to the negative 5. Alright, note that there's 1 barium for every barium chloride and 1 carbonate for every sodium carbonate. So the concentrations of these ions are the same as the concentration of the ionic compound. KSP is 3 times 10 to the negative 5. Well, KSP is 8.1 times 10 to the negative 9, as given previously. Q is 3 times 10 to the negative 5 times 2 times 10 to the negative 5, or 6 times 10 to the negative 10. Since Q is less than K, no precipitate forms in this case. All right. One last issue to consider in this type of problem is the quote-unquote common ion effect. Right. Consider, for example, copper 1 chloride, which is an insoluble chloride, and is dissolution into copper plus chloride. KSP for this reaction is 1.9 times 10 to the negative 7, and when we write down the equilibrium expression, that's equal to the concentration of copper times the concentration of chloride. Alright, let's consider finding the molar solubility of copper chloride in water. You should be able to do that without much difficulty. However, we will then consider a couple of wrinkles. Concentration of copper chloride in 0.2 molar hydrochloric acid, and in 0.15 molar calcium chloride. Calcium chloride, remember, is a soluble chloride. And remember, HCl is a strong acid. All right, you should at least be able to attempt A on your own. We will look at a solution to A and then solutions for B and C. Alright, solution for A, copper chloride in water, is a straightforward molar solubility problem similar to the ones you've already seen. An ice table has no concentration of copper and chloride initially. Since the stoichiometry for the dissolution is 1:1, the equilibrium concentration of each of these is X. And here X will be equal to the molar solubility. 1.9 times 10 to the negative 7 is thus X squared. When we plug X into the equilibrium expression, and that gives X is 4.4 times 10 to the negative 4. Alright, now let's consider B and C. Here, chloride is the quote-unquote common ion. In other words, in 0.2 molar HCl, the initial concentration of chloride ion is 0.2 molar. HCl is a strong acid. It completely breaks apart into H pluses and Cl's. Right? So while we still have a concentration of copper at 0, our chloride starting concentration is 0.2. Allow me to correct that typo here. In this case, X, which would be the copper concentration, or the copper, it is actually representing the molar solubility. If we assume x is small compared to the point 2, because we have a small k, that leaves us assuming a concentration of approximately 0.2 for chloride. Then 1.9 times 10 to the negative 7 is x times 0.2. X is 9.5 times 10 to the negative 7, which again would be the molar solubility. Note, by comparison to part A, that the molar solubility is much smaller in this hydrochloric acid solution. This is essentially an illustration of Le Chatelier's principle. The presence of the chloride, or presence of product, drives the reaction to the left. And we see a smaller amount of copper chloride dissolving. Alright, now let's consider the solubility in 0.15 molar calcium chloride. Now here it is necessary to remember that in a 0.15 molar calcium chloride concentration, the chloride concentration is twice 0.150. There are 2 chlorides in every calcium chloride. So the chloride concentration is 0.3 molar. Right, our table has no copper in it initially, but we have a 0.3 concentration of chloride. Pardon my correct typo, beg your pardon. The molar solubility is X, and once again we will treat the chloride concentration 0.3 plus X as approximately 0.3. Note that the increase in chloride concentration will decrease the molar solubility even further. Here the equation is 1.9 times 10 to the negative 7 is x times 0.3, giving a value of x, or a molar solubility, of 6.3 times 10 to the negative 7. Solubility decreases as chloride concentration increases. This is the common ion effect. It's a result of Le Chatelier's principle. This concludes the lecture for Module 4 of Unit 4.